Good day, I'm Dr. T. Welcome to my office, and today we are talking electricity and its cousin, magnetism, because in very many respects, they're two sides of the same coin. Actually, we've got a lot of things that are multiple sides of this same coin. But right now we're doing electricity and magnetism. Coming up soon we'll be doing light, which is kind of the two things together, getting a little bit weird. So, in order to understand electricity, I'm going to start out with electricity just because I got to start somewhere and it kind of helps to start with electricity. But I actually want to start with this idea of ways of thinking about electricity. So we're kind of getting into models. And what I want to do is this idea of field theory or of potential. Now, these are going to apply when we talk about electricity, magnetism, and gravity. And of course, anything that relates to them. So I kind of want to talk about them here real quick, but I want to do a little bit of a meta-narrative on top of these. Editor Dr. T here. In the original version of this video, there was like a 5-minute long rant on utilitarian versus realist views of models, specifically field theory and potential, as well as kind of a discussion of how that can be kind of taken into weird places, in particular by individuals who are not physicists, kind of general members of the population who see an idea that's very bizarre and maybe want to try and spice it up a bit because it honestly sounds like something you could spice up. And as educators that we probably want to caution against doing that kind of thing. But I'm going to cut that. So with that said, let's talk about magnetic fields and then potential. And I'm going to lean towards the potential because to me it makes a little bit more sense. But the idea of magnetic fields or electric fields or gravitational fields, and sorry if I keep calling it magnetic fields because that's usually where you talk about it the most. But field theory in general is that you've got these areas of influence that get described by lines emanating from a source, and they kind of arc around and you get nice little circles and whatnot. And I'll pop up a picture over here for an electric field. And basically these are describing the area of influence. Now, these are kind of going from one thing to another. A lot of textbooks will imply that these are like individual discrete lines like hairs or something. They're not. These are mathematical descriptions. Imagine like a contour map but written sideways. So you had like the paths down the mountain kind of thing. Just like on a contour map, unless you're in a region that's practicing a certain type of agriculture, you don't see a bunch of like lines on the mountains. You just see a mountain. The lines are added in to help us understand the slope of the mountain. The field lines and then the contour lines for the potential description are there to help us see what's going on. They're not physically there. So you've got this area of influence that's described by a series of lines arcing from one source to another or arcing in circles, etc. And you're going to be seeing these throughout the video. The main thing here, though, is these are not like hairs. They are not discrete, separate lines, and we're not describing each individual one. We are describing a more continuous field here. Okay, so the idea here, and let's talk electricity. We have positive and negative charge. The frustrating bit is we defined positive and negative charge before we understood what electrons and protons were. And I think I already kind of made this rant. I had that one KXED comic, I think I popped that up in the video, I'll pop it up here, where the guy goes back in time and says, hey, Ben Franklin, redefine charge this way and not the other way. But we defined charge before we knew what it was. We basically based it off of static electricity, which is you shuffle a bunch of electrons over and we get which one was which, inconveniently placed. But we're going to say electricity flows from positive to negative. And that is the convention. We always say it goes positive to negative, even though if you're dealing with electrons, it goes from negative to positive. The electrons are going from negative to positive, not positive to negative. Okay, but the electric current, we're going to say, is positive to negative. The math works just fine in either direction, so it doesn't matter. Okay, so I've got a series of field lines that are coming out of the positive one, and then they're going to arc around, and they're going to go into the negative one, and basically this is the path that charge flows. Now, alternatively, I could think of this in kind of a more plane-like. So I could imagine a two-dimensional plane. This is really 3 dimensions. We're adding an extra dimension, but there's no way to draw a picture in 4 dimensions. I mean, I guess you could do time or something, but we're just going to do a 2-dimensional plane. Keep in mind this is actually representing a 3-dimensional space. And that plane is going to be nice and flat. But then we're going to have some charge on it. And so the positive charge is going to be like a mountain coming out of that plane. And the negative charge is going to be a pit in the plane. And so the idea here is we're getting this idea that every point in space has a certain potential. Now that plane, we're going to call that 0 potential, but everything is relative. It's entirely from your point of view of the observer. So it would be both right and wrong to call that reference plane 0. It is its 0, but somebody someplace else may have a completely different 0. And when it comes into power transmission lines, that actually is a really big deal because the reference voltage at, say, the power plant may be a whole lot different than what's in your house, so you have to take steps to accommodate it. And that's why we have grounding. We stick into the ground, so we hook up to our local reference of literally the dirt around us. But that's a lot to say. Look at pretty picture. The idea here is when we're describing potential, this is not potential energy, this is part way to potential energy. When we're describing potential, we're looking at the difference in electric potential, what we're going to call voltage, between any 2 points on that plane. Now, if we know that difference, just like if we knew a difference in height, that is going to give us part of the information for understanding things like potential energy and flow of energy, etc. So this idea of there being a difference in electric potential between 2 different points, that's going to be voltage. And this is going to be one of those key things that we need to think about, that voltage is going to be a difference. It is never an absolute number. There are no absolute numbers in what we are dealing with. It's all relative. And I'm going to kind of keep coming back to this idea over and over again, which is very helpful for understanding electric current and how we set up our electric systems, etc. Okay, so if we look at this guy, what you'll notice is this slope between the two. The slope of these mountains / pits is entirely dependent on the material it's in. Are we in space, or are we in, say, a metal rod, etc.? The better the environment you have around you is at conducting electricity, the more shallow these are. Basically, you're going to be able to have a much longer range of influence for your electric field and thus connect a high, positive versus a low negative from farther and further apart. And that, of course, is going to be a good conductor. Things that are good conductors are going to have things that allow charge to flow. Metals are excellent conductors. You have electrons, you've got that electron C, they can flow. You have graphite, which is not a metal, but it's got that pi system, which is kind of pretending to be an electron C, and that allows electrons to flow. Likewise, you could have ions. And so if you have positive and negative ions, so cations and anions, those can flow if they are able to move. Solutions that have these ions, or something that goes into a solution to create ions, we call those electrolytes. And for biological electricity, we don't have little wires in us. Okay, most of us don't have little wires in us, some of us do. But most of us don't have little wires in us. Instead, our nerves are conducting electricity by the flow of ions. So they're using electrolytes. So that's why those are relevant for biological systems. If you don't make those cations and anions, then you are going to be a non-electrolyte. Or if you don't have some kind of mobile electrons, you're going to be an insulator. So things that have mobile charge, those are going to be good conductors, whereas things that have a very stationary charge, things that don't go moving around, those are going to be very good insulators. So insulators are going to cause very steep peaks in this potential. Basically, if you're far away, you're not getting any electric current because effectively you're away from the mountain or away from the pit. Whereas if you have a good conductor, it's going to be much broader, and now the mountain can connect to the pit and you can get yourself a nice flow of electrons. So let's talk about actually using electricity. Generally speaking, we've got a couple of different things we want to bring in terms when discussing electricity. The first one I'm going to bring up is Ohm's law. And this one is usually fairly humorously described by a comic similar to this. We've already met one of the terms. This is V for voltage. This is the potential difference. between two sources. If we are talking your electrical outlet, this is the difference in potential between one of the flat plugs and the other flat plugs. The bottom bar, the ground, is a safety device, and we're going to kind of ignore the ground pin. But this is going to be the difference between the two. Now, there's more going on, of course. We also have a flow of charge. If we're going to conduct electricity, we're going to actually move some charge. The charge actually has to move in order to get any energy moving. Or you have to have the potential for that charge to move to have a potential energy kind of thing. That's given the term of current, and the unit for that is going to be amps. So that's going to be the amount of charge, which we give in coulombs per second. Inconveniently, a coulomb is not a mole of electrons. I wish it was. It would be so much convenient, but this is before we got everything sorted out. Voltage is in the unit of volts. Yeah, makes sense. And the last term is resistance, which is the unit of ohms. Resistance is basically how hard it is to flow through the material. Really good conductors, the resistance is going to be really low. Insulators, it's going to be really, really high. And as such, if you want to move a certain amount of current through something, then you're going to have a lot of voltage. Now, the interesting feature is, if you get enough voltage, then even your insulators aren't insulators. You know, you can still get the current through. Picture behind me, we got some lightning going on. You crank the voltage high enough, air is a good insulator. Well, it's not that good of an insulator. So anything can be a conductor if you crank the voltage high enough. You know, if the mountain's big enough and the pit's deep enough, they're going to connect no matter what. And so if we look at this one, we get this idea of voltage equals current times resistance. And this gives us a couple really interesting features to start thinking about when we start thinking about delivering electric power to places. So the formula for the amount of energy transferred with electricity is going to be volts times current. Basically, the volt is describing like the height you fell from, so how much energy per unit of charge, and current is going to be describing charge per second. So we get energy per second, which is power. Now, the equation is fairly straightforward. Power, usually given in watts, is going to equal the voltage times the current. Voltage in volts, current in amps, and this is actually something fairly straightforward. You can look at your light bulb, you read the power rating, not the equivalent to, but the actual power rating on the light bulb, and you can figure out how much current and it's going to draw at a given voltage. Now, here's where things start to get interesting as we start merging these equations together. Turns out, current has some interesting side effects. As current is traveling through a wire, it's going to create a magnetic field. I'm going to get to that later, but that field, that area of influence, is also able to create current in other wires. It's able to have some energy leak from this. You may have seen those pictures of like light bulbs underneath a high power line and they're lighting up just from the magnetic fields of the power line. So that's some leaking off energy. But also, as the electrons are moving, or as the ions are moving through, they're bumping around and they're going to be generating some heat. So you're going to be losing energy in the form of heat. So if you want efficiency, you want high voltage, low current. But remember, anything is a conductor at a high enough voltage. So the higher the voltage, the more things start conducting that you would really rather not. Thus, we get into an interesting set of trade-offs. I would like to move lots of energy at a fairly high voltage, but I would rather not have a fairly high voltage for safety reasons. And thus, we are going to start doing some interesting ways of thinking about adjusting voltage and current in order to optimize our systems and make better setups. But in order to do that, I need to talk about how power is generated and its relationship to magnetic fields. Let's talk circuits, and that will tap us into the wonderful world of power generation. Now, we're going to be moving electrons. If we take an electron and we move it over, there's going to be a gap left where it once was. We call that gap the hole. Now, the electrons are going to go one way, and the hole is going to sit there. Now, if you just kept pumping electrons and building up more and more holes, the holes would be positively charged because they're probably sitting next to a nucleus of some sort, and the electrons are negatively charged, so you're building up positive on one end and negative on the other end. Opposites attract each other, like repels. You can build up a positive charge on one end and a negative charge on the other end. That works well, but you're creating a voltage between the two. So it's going to be harder and harder to keep doing that, and eventually they're going to want to flow backwards. We call this a capacitor. This is also how lightning works. Unless we want a capacitor where we store up that charge differential, we're going to want to have a way of filling in those holes. Let the holes move away so they can meet up with the electrons. By the way, if that sounds kind of weird, think about everyone standing in a line. One person moves forward, there's a gap. The next person moves forward, the gap moves backwards. Yeah, it's not a physical thing, it's a lack of a physical thing, but we can track the gap in the line. Now, if we made the line a big circle, as one person moves forward, everyone takes a step forward, and the gap does a lap all the way back, and the person who moved forward is filling up the gap. It's a weird line, kind of like a duck, duck, goose game, I guess. Well, we can do that with circuits. If we have our electrical conductive material in a circle, then the electrons can go around the circle and we don't build up charge in any one spot. We don't build any capacitors that would shut down our circuit. Yay! This can actually be useful. We can get the flow of electricity without having any weird bottlenecks, etc. Now, if we were to disconnect that circuit, we were to open it up, well, now we'd have a disconnect and electrons would pile up on one end of the gap and holes would pile up on the other end of the gap, and the electricity would stop flowing very quickly because you'd have to increase the voltage continuously to keep that piling going up. So we're going to close our circuit. We're going to have a nice circle to get our circuit in, and let's talk about a few things for circles, but let's use water for a metaphor. So here's a water-based circuit. The height of the water is going to be the electric potential. On one part, we're going to have a pump of some sort, something to increase the electric potential of our electrons. And then at the other end, we're going to have some form of load. This is something that's going to be extracting the energy from the electricity. In this case, we got like a little waterfall or a water chute, but this could be something like a light bulb or a heater, etc. This area, by the way, is going to have a lot of resistance. It's resisting the flow of electrons because it's extracting the energy out of them. Now, we've got our circuit. The water's pumping up, it's doing a lap on the top, it's falling down the load side, and it's going around the bottom and getting pumped up. So, let's talk about what we can do with this. I guess the first thing we should talk about is how do we make a pump? We actually have a lot of options. The simplest and kind of the first anthropogenic electric source, because lightning and eels existed long before people were forming electric circuits. The earliest anthropogenic one is going to be the electrochemical cell, a battery. Although I should point out, technically speaking, a battery is 2 electrochemical cells or more. It actually comes from the battery of cannons. So you have a cannon, or you have 2 or more cannons, which is a battery. The AA or AAA batteries, those are actually not batteries. Those are electrochemical cells because they're only one cell. So let's look at the parts of this. What we're going to do is we're going to take a redox reaction. It can be a single displacement reaction, which are kind of the easiest ones to draw, but it doesn't have to be. You can even do things like combustion and build a fuel cell. Fuel cells are conceptually very similar to batteries. They're not batteries, but they're a lot like one. Okay, so in this case, what we're going to do is we're going to do the redox side of the reaction on one side. That's going to give us some electrons. It's going to shove across the wire. That's our electric circuit. And then we're going to get to the other side of the battery, which is going to be our oxidation reaction. We're going to suck up the electrons. Now, in this process, we're going to generate cations on the reduction side, and we're going to suck up cations on the oxidation side. So we either need to shovel cations around or maybe just shovel anions around. We've got to move some ions one way or another, and we're going to use a membrane or a salt bridge. Either way, we need some way to balance the charge, because remember, we have to have electricity as a circle. The circle has to go through the battery. It can't start and stop with the part of the battery. So that membrane or salt bridge is going to be the completion of the circuit. Now, we can stack these together just like you'd have one water pump up to a height and another water pump up to a height, or we can put them side by side. Speaking of which, let's talk about circuits, serial and parallel. So if the circuit is in parallel, that's going to be side by side. Now this one, the loads are in parallel. And so you've got the energy being pumped up, you've got the increased voltage, and it's going down two different loads. They're side by side. Each one's getting half the current, or in this case, half the water flow, but they get the same drop. They get the same voltage. The alternative, of course, is in series. In series, you've got kind of this stepped waterfall, one after the other. They get the exact same current, but each one gets a part of the voltage, or a part of the drop. In this case, it's shown as half. It doesn't strictly have to be half. Now, same story basically goes if I do the source, the battery, or whatever. If I put them in series, I'm going to get the same current, but instead of cutting my voltage in half, I'm going to add them together. So one battery boosts it, the next battery boosts it even higher. If I put them in parallel, I can get twice the current, but I get the same voltage. Pay attention to things that use AA batteries. If you look at the orientation, they're almost always in series. So each one's not a battery, but your TV remote is, effectively. And it's because it wants to run at a slightly higher voltage than the voltage of the AA battery. So if you put two of them in series, you're going to get double the voltage. You put four of them in series, you're going to get quadruple the voltage. Fairly straightforward. Of course, batteries are not the only way to make electricity. We have a few other options. For instance, we can do a solar cell. In the solar cell, we're going to take a couple layers of material. We've got p-doped and n-doped. Basically, these are metal or silicon that has different elements enriched into them, and it's going to change their electric nature just a bit. We're going to use the energy from a photon to hit that. That is going to cause the electron to be kicked off of an atom, effectively creating an electron-hole pair. And the way the guy is set up, the electron goes one way, the hole goes the other way, and they go around the circuit so the two of them can meet up and the electron can fit the hole. Side note, LEDs basically work the exact same way, but in reverse. You have to build a completely different chip. You can't have the same silicon do one or the other, but the same physical concept is roughly the same as a solar cell in reverse for an LED. We can have the same basic concept, but instead of using photons, we can use jiggling of heat. So this is a thermoelectric generator. You've got two different types of metal, and you're having this gap with your two different types of metal, and heat flowing from one side to the other will induce an electric current going through here. That said, the main way we make our electricity is with spinning magnets. Okay, so that means I need to talk about magnetic fields. Okay, so let's talk about magnetic fields. These are an area of influence. Once again, we've got ourselves a field line, and you get them whenever you have a current, so moving charge. Interesting enough, permanent magnets, the moving charge is actually the electrons buzzing around the iron or neodymium atoms. Okay, so we're going to do electromagnet. If I've got myself a wire, as current is flowing through it, it's going to create a magnetic field around it. But in classic physics fashion, if I can create a field, then a field can create the current. So I could reverse everything. Everything is completely reversible. So let's start building an electromagnet, and then we're going to use our electromagnet to figure out how we can reverse everything and make ourselves a power source. Okay, so that magnetic field, unless it's a lot of current, is not that strong. So I want to kind of amp it up. So if I make a loop in my wire, turns out if I loop my wire, then all the magnetic fields happen to be spiraling around them because they're going in a circle around the wire, such that they kind of line up in the middle. This could be useful. So I can start coiling my wire, maybe put a metal core in the middle to help focus the magnetic field lines. And now all of a sudden, I've amplified my field quite a bit because I'm stacking multiple fields up together. They're all going the same way, so they're going to add together. Sweet, I've got myself an electromagnet. If I have an electric current on there, my magnet turns on. If I don't, it doesn't. This is how those door stops connected to the fire alarm works. So if you go into a commercial building, you'll see your doors are propped open and they have these little pads on the wall. And these guys have an electromagnet in them. So when the power is on and everything's good, the electromagnet's on and it holds the door open for you. Great. If the power goes off or the fire alarm turns on and it turns off the power, no magnetic field, the door shuts. The idea now is if something's gone wrong, you probably want the door shut so that the fire gets stopped by the door and gives the firefighters and the sprinklers more time to make it go away. Okay, so now we've got ourselves an electromagnet. We can make door stops. Let's expand this because we could turn this into a motor. I'm getting to generators. We got to go through motors first. Okay, so what I can do is I can take my magnetic field and I can pull my magnet closer to it. And I'm going to build this up. I'm going to have an outside part that I'm going to call the stator. It's not going to move. And I'm going to have an inside part I'm going to call the rotor because it's going to rotate. We are not original here. Okay, so I'm going to put a magnet on the stator. And then in the rotor, I'm going to put some coils of wire. And I'm going to set them up so that I've got two wires coming in, but they're offset. So I've got my positive and my negative wire. Currently, I'm still going to be using what I call direct current. So far, I've only been describing this idea of direct current. And that's where the electrons all go around the circuit in the same direction. They just continually go around in the same direction. You can kind of guess that there's another version where they go back and forth, back and forth. That's called alternating current. We'll get there. Okay, so I'm going to have that. And if I had my magnet, direct current's going to give me my nice consistent magnetic field, and it's going to pull north to south, and it's going to stick. Now, if I just want to like shove something out a tube, that would work, and we call that a servo. Those are particularly useful things. But I want it to spin, because I want to drive wheels and stuff, or clocks. And to make it spin, well, I can get it to go in one direction pretty quickly. So if I've got those, I connect the power such that the magnetic field created by my coils is going to be pointing north to north and south to south, and that's going to cause it to spin so that it doesn't do that. And then that way it'll point north to south, north to south. There's a problem, it stopped spinning. So I made half a turn. So what I'm going to do is I'm going to wire this up so that my two input ones, when they connect to my rotor, they're going to have little brushes, usually made out of graphite. But when they connect to my rotor, I'm going to have it so that they rewire. One connects to one side, one connects to the other side. So once the rotor turns, all of a sudden the wires switch which input they're hooked to. So what was the negative side now becomes the positive, and the positive becomes the negative. And all of a sudden, my magnetic field reversed. I reversed the flow of current through my coils, so my magnetic field reverses. And lo and behold, I am not north to south, south to north. I am north to north and south to south. So it spins. And repeat, repeat, repeat. And we got this thing spinning. Yay! We've made ourselves a DC motor. Now, I had a toy submarine that I sold years and years ago. But as a kid, I liked my toy submarine, and it had lights and a little periscope that went up and down and wheels, and you put in some batteries and it would like run across the floor blinking and doing stuff. But what I learned is that if I didn't have any batteries, I could push it across the floor and the lights would light up and the periscope would go up and down and the little fins would flap. Because it turns out in physics everything is reversible. It was running on DC, and DC motors are also DC generators. Sometimes we call them dynamos. Okay, so if instead of taking the setup and using the electric current and magnetic fields to spin the rotor, if I use some other force, like child bee's hands pushing across my submarine and making its wheels spin as it digs into the carpet, then we can use the rotation of the rotor to interact with the magnetic field to generate the electric current. Everything runs in reverse. Now, how do we want to make this thing spin? Oh, you've got options. You want to put some blades and make it a windmill? Awesome. You want to put a turbine and have water flow over it? Awesome. You want to boil water, use a turbine, and then have it spin? That's frankly how we do most power. Although, I'll get to that. Turns out we usually do AC, not DC, for reasons that I'll explain here shortly. But this is a way of going ahead and making ourselves a nice power source. Okay, let's talk AC. I keep putting this thing off. So in alternating current, the general idea is that we're going to go forward, then backward, and then forward, and then backward with our current. This actually is somewhat more convenient for making some types of motors, and you get some advantages to doing this. Remember how in the DC motor, you're going to have to rewire it as it spins in order to switch the polarity of your magnet, making it going from one direction to the other? Well, if your electric field just goes one way and then back the other way, you don't actually have to do that. In fact, you can put the coils on the stator pretty easily. So we can make ourselves a motor basically by alternating the current that goes into it, and we can have the magnet in the motor spin. The reasons we like AC ends up having to do a bit with how these motors work. Or I should say, the generators. Let's look at an AC generator. Generally, AC generator, you're meaning AC. Same basic idea. We got the magnet on the outside. We could use a big permanent magnet, or we could use an electromagnet. Typically, if we want big, we're going to go an electromagnet. So if you've got an AC generator, then it's almost certainly going to have a small DC dynamo powering a fairly powerful DC magnet that's actually running the AC generator. So you can I believe you can power them off the same shaft. I haven't dived into it. There's the one guy that runs a hydroelectric dam that's got a YouTube channel, something about wet beavers. So I'll let you check him out, although not the most family-friendly video series. I will warn you of that. Okay, so here's a picture of an AC generator. Notice this guy is simpler. We don't have any weird wiring. Basically, one side of the coil, which is inside the rotor, that goes to one brush. The other one goes to the other brush. But as it rotates, hey, the field is going to go back and forth because, once again, you're going north to north, south to north. So you've got that alternating field. This makes it a little bit simpler to make. And we can do one more interesting quick trick when it comes to AC power. This thing. Yeah, what am I looking at? What you're looking at is an AC generator and an AC motor hooked together with no moving parts. What? Okay, let's look at an AC motor. Back to this picture. The coils are on the stator. Let's look at an AC generator. The coils are on the rotor. What if we stick the rotor from an AC generator in the stator of an AC motor? Fun fact, because the electric current in the AC motor is alternating, I don't actually need to have the thing spin. And because iron works really well with all those electrons that can line themselves up in their tiny little magnetic fields, I don't actually have to put my stator and my motor one inside the other. I can go back to this kind of shape. Why would I want to do such a thing? This is absolutely nuts. I'm making electricity from electricity. Why don't I just use the electricity I have before? Well, notice the picture. The number of coils aren't the same. This is actually a really big deal. See, the magnetic field, the intensity of the magnetic field is proportional to how many coils you have. This means that depending on the number of windings you put in and the number of windings that come out, you can change the voltage. Okay, this guy is called a transformer, and this basically is why AC current won the current wars back in the late 19th century. What's going on here is that I can put in a low voltage and I can get out a high voltage, or I can put out a high voltage and get in a low voltage. Remember all the way back when I said this. So if you want efficiency, you want high voltage, low current. But remember, anything is a conductor at a high enough voltage. So the higher the voltage, the more things start conducting that you would really rather not. Thus, we get into an interesting set of trade-offs. I would like to move lots of energy at a fairly high voltage, but I would rather not have a fairly high voltage for safety reasons. Well, we want to keep the voltage high if we're going to transfer it a long distance. We want to have voltage at our house relatively low. This way, we can easily change the voltage from high to low or low to high, depending on where we are moving our electricity from, thereby increasing efficiency, but also increasing safety. Lower voltage, generally speaking, safer. Higher voltage, generally speaking, more efficient. And thus, we get this nice trade-off with AC. And this makes things very nice. Also, in general, AC generators work a little bit more efficiently. Okay, last thing I want to discuss. We've talked about AC and DC current. Certain systems are going to definitely prefer one or the other. If you're spinning a motor or lighting up old school lights, it doesn't necessarily matter which one you're using. Specific motors need specific current. So an AC motor works with AC, it will not work with DC, and vice versa. AC motors do tend to work a bit better, so we do tend to jump into those. Side note, when I talked about AC, I didn't jump into the idea of phases. Basically, the back and forth thing, as you noticed on the picture of the generator, well, that would give you up, down, up, down. We would call that a single phase. That's kind of flat. There's plenty of room to put more stuff on that. So I could put a whole different set of windings on that guy. And with my same turning system, I could create another wire that's going up, down. But it would be going kind of up, down, just slightly out of sync. Typically, we do 3 sets of wires here, so we get what we call 3-phase power. It's nice in that their magnetic fields cancel each other out, so as you're putting them along the wires, the magnetic fields are going to cancel themselves out, which reduces the impact to the local environment and produces greater efficiency. Now, I may very well have AC energy, but I might want DC energy. Things like electronics, anything involving silicon, that is going to need DC power. Things like solar cells and batteries, those are also going to be exclusively DC, and maybe I want AC power. So how do I convert these? Well, I can use a rectifier to go from AC to DC. Basically, it takes the push-pull and makes it to a push and a pull. If you notice, almost all of your electronic devices are going to have some kind of like little box. So the charger for your USB, you know, the thing that plugs in the wall, how it's a box that you plug your USB cable into, the main thing inside of there is a rectifier. It's actually got a lot going on there, but the core part is a rectifier. If you've got an older style laptop that doesn't use the USB, which is actually still pretty common, then in that case, you'll notice there's kind of a bulge somewhere in the wire. That's the rectifier. Now, let's say I want to be all fancy and I want to have solar panels and I want to power my refrigerator. My refrigerator is optimized with AC motors. Yeah, they're pumping and squishing gas to make it a refrigerator. So how am I going to power that? I need something that takes a stream and I convert it into a push-pull. And that thing is an inverter. Interestingly enough, inverters are one of the major costs for a solar power system. Basically, you're spending a lot on solar panels as well as a lot on the inverter, and potentially a lot on batteries, depending if you're running a battery-based system or not. Okay, so that's kind of the highlight. That's where I wanted to get to with this video. In the next video, I'm going to talk about the wonderful world of waves, and then later we're going to finish up physics with heat and heat transfer. So with that said, have a wonderful day, and I will see you in future videos.